So in the last few classes, we have looked at various principles of hydrostatics and in general fluid statics. In this particular class, we will look at fluids under rigid body motion. So fluids under rigid body motion refers to flows in which the fluid either translates or rotates like a rigid body. We have already seen that in order to have deformation, we need a gradient in the velocity field. And this meant that if we have a fluid element like this, and if you have a higher relative velocity of the top face with respect to the bottom face, it would lead to a deformation of the fluid element. However, if both the velocities are equal, then the fluid body would simply translate without any deformation. So now let us look into the theory of it. We've already seen that the body force acting on the fluid is equal to minus gradient of the pressure, and we have looked at the interpretation of the negative pressure gradient. However, if the fluid is undergoing rigid body motion, this force must be equal to the rate of change of linear momentum of that object. So in general it could be mass times acceleration, but we recall that this force is per unit volume. This force was evaluated on a per unit volume basis. So it will be mass times acceleration of that element per unit volume. And so it would simply boil down to rho times A. So we have rho A is equal to minus grad P. Now let us consider a flow with a constant acceleration. So this would imply rho Ax is equal to minus del P del x. I'm just expanding this particular equation. Then we would have rho Ay is equal to minus del P del y, and similarly we will have rho Az will be equal to minus del P del z, but there will be another added body force that will be due to gravity minus rho G. So here I have explicitly not written gravity, but in general the force acting on a fluid element is due to the pressure gradient and the action of its body weight, that is gravity. So plus rho G, but when we substitute that G is equal to minus G acting in the Ez direction, we obtain this particular relationship. So these are the three equations which govern. So now let us look at how we can use these equations to solve a very simple problem, that of a sloshing tank. Let us consider a tank as shown in the problem. Now the tank is moving at some acceleration, and there is a level of water in this, and so when the fluid accelerates, we know from experience that the fluid will be pushed towards the back in the frame moving with the vehicle. And there are various examples where you can see this when you are trying to have a cup of coffee or trying to drink water inside a moving car. When the car moves with a constant velocity, that is when it's not accelerating or decelerating, the level of water remains fixed. However, the moment the car accelerates or decelerates, in order to avoid a bump or in order to overtake someone, you will see that the level of water shifts and it becomes difficult for you to drink water. So because of this acceleration, the liquid would become something like this. So the question is, what is the equation of this particular free surface of the liquid? So the way to do it, let us first identify the fact that all the points on the free surface are at ambient pressure. Meaning all over the interface between the water and the, so this is water, this is air. So all at all points on the interface, the pressure will be constant. So I can write at any point. So let me call this axis as x and let me call this axis as y. So not y, let us use the convention used before, and that will be z. So dp in this coordinate system can be written as del p del x dx plus del p del z dz, and this statement is true regardless of whatever is going on. Now from the previous equations we know that del p del x is going to be equal to, or rather minus del p del x is rho ax and minus del p del z is equal to minus rho g, and if there is some other acceleration plus rho az. So this follows from the previous equation. Oh, rather minus del p del z equal to rho az plus rho g. So I have made a small sign mistake. That's okay. So now let us substitute these equations over here, and in fact in the given problem we only have ax, az is equal to 0. So this particular expression becomes rho g, and it is given that the value of the acceleration is equal to 0.5 times gravity. So this will be equal to rho times g upon 2. So from these two equations we may write del p del x equal to minus rho g upon 2 and del p del z is equal to minus rho g. Consequently, in this particular equation we can then write dp as minus rho g upon 2 dx plus minus rho g times dz. Now recognizing that all over the interface the pressure is going to be a constant, when I write this equation at the interface, so for any point on the interface we have dp is equal to 0, because over the interface, I reiterate, over the interface the pressure is ambient pressure and it does not change with x and y on the interface. So these are all the points on the interface. So the choice of x and y are such that the x and y constrain the point to be on the interface, not anywhere else randomly. Okay, they will constrain it to be on the interface. So at the interface dp is equal to 0. So we have 0 is equal to rho g upon 2 dx plus rho g dz. This implies at the interface dz upon dx is going to be equal to, so we've taken this on the left hand side, so minus rho g upon 2, and that thing will be divided by g rho g. So this becomes minus half. So thus if we integrate this equation we have dz dx equal to minus half, right, and this implies that z is equal to minus x upon 2 plus constant. So it's like, and this is an equation for a line with a negative half slope with a certain intercept. And the way to find the intercept is that given this shape exists, given the dimensions of the vehicle, I can find out the volume of water in the deformed condition in terms of the offset, and I know how much volume already existed in the vehicle or in the tank mounted on the vehicle in the initial time. Because there is no water sloshing out as such, we can equate these two volumes and evaluate the value of the constant. It is as simple as that. So let us proceed with finding out. So this was one kind of motion where it was a rectilinear motion. We can have another kind of motion where we can take a beaker containing a liquid and then we spin the beaker on a turntable. And as a child, you might have done something like this. I mean, even as an adult, you could have tried something like this, no problem. So initially, if there is no rotation, the fluid remains flat. Upon rotation, you will observe that the fluid gets thrown to the side and there is a kind of parabola or rather paraboloid that starts forming in the fluid. Notably, the entire fluid rotates with the same velocity as the velocity of the turntable, but it is not instantaneously the case. When the turntable starts rotating, the effect of viscosity begins to propagate into the fluid, and after a while, the entire fluid begins to rotate with the same velocity. However, these discussions will be more understood when we consider what viscosity and viscous propagation is. For now, it is sufficient to know that this kind of rotation makes the body move with a constant velocity. So let us assume that the entire beaker is rotating with a rotational velocity omega. Our task is to find out the equation of this particular shape. And it is important for us to acknowledge that this problem is an axisymmetric problem, meaning if I draw a 2D diagram of this, and if this is the interface shape, I can choose a coordinate system, something like this. This can be r and this can be z. And the theta angle does not appear in our problem. So now we have to rewrite the equations of motion in the RZ coordinate system. So once again, for any point we can write dp as, now it will be del p del r dr plus del p del z dz. So this is the dp in a cylindrical polar coordinate system. Now we can write in a straightforward manner that del rho times az is going to be minus del p del z minus rho times g, and this is true. However, there is no acceleration of the beaker in the z direction. The only force acting on the fluid elements in the z direction will be that due to gravity. Thus, this particular term will vanish. So we have del p del z is equal to minus rho g. Similarly, because of the rotation of the beaker, a fluid element at a given distance r will experience a centripetal acceleration as seen from the lab coordinate system, and the magnitude of that acceleration will be omega square r, and the direction will be opposite to the radial direction. So the radial direction is always pointing away from the beaker. So instead of that, it will be pointing inwards. So rho times ax, or rather not, it will not be ax, it will be ar, is actually minus rho omega square r. This is the acceleration on a fluid element in a in this rotating beaker. So we have this equal to minus del p del r. Okay. So fundamentally these two are equal and these two are equal. That is how we have arrived at this particular expression. So thus we have del p del r is equal to rho omega square r. So with the help of these two expressions, we can now substitute them in the expression for dp. So we have dp, and again at the given interface dp will be 0. At the interface dp will be 0, meaning the choice of r and z on the interface will be such that we always lie on the interface. R and z cannot be arbitrarily chosen. Okay, so dp equal to 0 at the interface. This implies this equal to del p del r times dr. So rho omega square r dr plus del p del z dz. So del p del z is minus rho g dz. So when this is equal to 0, we have rho omega square r dr is equal to rho g dz, and essentially we have dz upon dr, or I mean we can simply integrate it at this point itself. So essentially we have rho omega square r square upon 2 is equal to rho g z plus a constant of integration. Okay, now one easy way of finding out the constant of integration is attaching the coordinate system at the minimal point of the parabola. So obviously this equation describes a parabola where c is simply an additive offset in the z coordinate. C is just an additive constant in the z coordinate. So I can very well choose the coordinate system to be something like this, so that z equal to 0 corresponds to the bottom point, and essentially z equal to 0 corresponds to p is equal to p atmosphere. So essentially I can simply make the constant to be 0, and I will have rho omega square r square upon 2 is equal to rho gz, and this is the equation of the interface. I can cancel out rho, no problem. So essentially at z equal to 0 we have r equal to 0 and p equal to p atmosphere. For all the other points we can find out the pressure. How can I find out the pressure at some other point? Well, we can simply write down the expression for dp and integrate it over these 2 points. Essentially dp is rho omega square r dr minus rho g dz, and p is thus rho omega square r square by 2 minus rho gz plus constant, and the constant that we have chosen is such that in this particular coordinate system r equal to 0, z equal to 0 correspond to p equal to p atm. So the constant when r equal to 0, z equal to 0 becomes p atmosphere. Therefore we have p minus p atmosphere is equal to rho omega square r square by 2 minus rho g z. And with the help of this particular equation, you can put in any r and z you want, and that will evaluate the pressure at that given point. Okay, so this is how you do it. But remember, at all the points on the interface, p you will find out that it is exactly equal to P atmosphere, because these are all the points on the interface. All the points on the interface are parameterized by a combination of R and Z which satisfy this particular equation. So if this particular equation satisfies the equation of the interface, you can substitute exactly this expression over here, and the right hand side will become 0, implying P equal to P atmosphere on the interface. So both these equations are consistent, but this equation can help you find out the pressure at this point or at this point or at this point, any point. Okay guys, any doubt so far?
Sir, just a basic doubt.
Yeah.
Can you explain why at the interface is given to zero in case of rotating?
Can you repeat the question? I could not get.
But can you just explain why the dp would be zero at interface in this case?
So dp is by its very definition. Okay, so the interface between any two fluids. So if this is air, rather this is water, this is air. Given that this interface exists, there must be some forces acting on the interface which have caused the interface to become like this. But atmospheric pressure acts equally at all points, meaning, okay, first of all, let us assume that these differences in altitudes are not humongous. They can be at best 1 meter, 2 meter, doesn't matter. So the added pressure on top of the atmospheric pressure because of a column of air that is 1 meter high will be negligible. So the pressure contribution rho air GH as compared to P atmosphere. Let us look at this. So what is rho air? 1.3 kg per meter cube. What is density? It is so the gravity is 10 and say height is 1 meter. So this becomes a pressure of 13 Pascal, whereas P atmosphere is 101,325 Pascal. So it is just a very small fraction of the atmospheric pressure. So you can very well assume that all the points on the free interface are at the atmospheric pressure. In fact, even if you take a column of air of 100 meters, right, hardly anything changes. That is why you can assume that assumption to be true. So all the points on the interface are at the atmospheric pressure. Well, they are approximately equal to the atmospheric pressure, and hence at any 2 points on the interface, if I move along the interface, dp has to be equal to 0. Is it clear?
Yes, yes.
Yeah. So these kind of things where one quantity is significantly larger than the other quantity, these are, I mean, if you want to rigorously prove all this, you can do something called as a regular perturbation. And hopefully somewhere down the line, even if I don't cover it in the class, I will do something of a video for my other purpose. Okay, so it will be useful for you guys eventually. So any other doubt?
Regular perturbation.
Hmm?
What is this thing you introduced? Regular perturbation.
It will be discussed in more details in some other video. Actually, I do have some videos on this on my YouTube channel. So it was a part of one of the advanced fluid mechanics course. So you can have a look. It makes use of an open source MATLAB clone called as GNU Octave. You can have a look sometime if you have it.
Sir, please add the link in the note.
I'll do it. And most importantly, don't forget to like, share, subscribe. Okay, it helps me. I don't get any money, but motivation. So now we move on to fluid kinematics. So before that, a very small preface about fluid kinematics. So understanding the various forces or the nature of forces acting on a fluid element are important to gauge what kind of behavior a certain flow will have. However, we have already seen that shear stress, for example, is set up when there is a kind of shear strain or a rate of shear strain on the fluid element. So, in order to understand how stresses are set up in a fluid, we must also understand how rate of strains are also set up. And rate of strains, as we had earlier seen, are somehow related to the gradients in the velocity. So it is important for us to understand how the velocity field can be described in a given flow. And so fluid kinematics is that branch of fluid mechanics in which we will attempt to describe fluid motion without referring to the nature of the forces acting on the fluid. We want to just express how the motion is. So before moving to that, let us quickly recap what different kinds of fields are. So we can have a scalar field or a vector field. So a scalar field, for example, pressure. So we can have a domain, and given that it's a field, pressure can in general be a function of x, y, z, and it can vary in time as well. So it's a continuous field over space and time. Temperature is one more example, density is another example. Vector field. So at all the points we have a continuous variation of the velocity, and at a given point I can represent the vector field as the three components of the vector in the unit directions. So in this case it can be E1 direction, E2 direction, E3 direction. And each component of the vector field, so for example, we typically represent the velocity vector field as Ui plus Vj plus Wk. So each component of this vector field is also a scalar field. So this is a scalar field, this is a scalar field, and this is a scalar field. But each component represents sort of the projection along the I, J, and K directions. I, J, and K will interchangeably be used as Ex, Ey, and Ez directions, or sometimes E1, E2, and E3 directions. But invariably you will find the velocity components as U, V, W, or U1 or V1, V2, V3, or it can also be Ux, Uy, Uz, representing the velocity in the x direction, velocity in the y direction, velocity in the z direction. This is actually a superscript, subscript rather. So this is how we will work with. We will work with fields, and it brings us to a very important consideration, that of a Lagrangian description of motion versus an Eulerian description of motion. Now in classical mechanics, we can track a given particle. So if we have a particle, if there is some force acting on it, we can perform time stepping for that particle, and that particle can move in the entire domain. So the particle moves on this particular track. When we identify this particle in particular, that is, we have identified that this particle, say m1, so we will always sort of track m1 as it is going through the domain. Now this m1 is a fluid particle, meaning it need not retain its shape, it can deform and it can leave the domain. And how much it will deform will sort of depend on the velocity gradients that this fluid particle experiences at all the given points during its trajectory. So in order to describe a single identified particle, this particular framework is called as the Lagrangian framework. And this is what you might have done in classical mechanics. So how do we find out how the particle is going, what the trajectory is, and so on? We will say that the initial location is at x naught, y naught, z naught at some time t. So this is pardon me. So this is like the initial location of the particle. Now, how would I describe the motion of the particle? So the u velocity at this point, u velocity at a given point is equal to the rate of change of x at that given point. And the reason why I'm not writing the acceleration is because the acceleration falls beyond the purview of fluid kinematics. This kinematics does not want to involve the forces. So the u velocity at this point is dx dt, and with the help of this we can integrate dx from some initial condition to a later condition as integral u at that particular point times dt, going from t naught to some other time. And because we are integrating them to x and t, we must make them as dummy variables of integration. It's a very trivial task to do this. There is nothing sacrosanct about this particular expression. Similarly, we can have the v velocity at xyz, and that will be equal to dy dt, and the w velocity at xyz, that will be equal to dz dt. So at this particular point, if this is the velocity, then at the next time we can integrate it from, suppose this is x naught, y naught, z naught at a time t naught, then at a time t it will arrive at this point and the new location will be x1, y1, z1. If I call this as x1, y1, z1, I can very well write this as x1 and t1. Now once it reaches point t and the new coordinate x1, y1, z1, now we would have to re-evaluate x, the u, the v and the w component of the velocity at the new point, and with the help of that we can again perform such an integration to again move forward in time. So if this is t1, we can go to t2, then again at this particular point we will look what kind of velocity does the particle see. So here the particle will see a very small y velocity, but it will only see dominantly an x velocity, so it will move along x primarily. Over here the particle will see a x velocity and a y velocity, that is it will see a u and a v, and so it will again try to go up, and again here it will see a y velocity, and like this. So at each point you are sort of sampling what the velocity of the flow is, and as we go along the trajectory we are sampling velocities along the trajectory. But is it simply sampling the velocity along the trajectory? No, it is not. It is sampling the velocity at along the trajectory at the time when the particle arrives at that given point in the trajectory. So This means that if this is the trajectory, I want to know what, so if the particle is here at time t naught, I want to know what the velocity is at this point at some t3. Now I cannot say what the velocity at this point at time t3 will be unless the particle, when moving along its trajectory, identically coincides with this point at a given time t3. This essentially means that if I want to know the velocity at this at time t naught, while the particle exists only at this point, I am simply focusing my attention at this particular point in the domain, and hence I will only know the velocity at this particular point at time t naught. I will arrive at this particular point at time t2, and hence I will be able to say that the velocity at this particular point is so and so, or rather so and so, at a time t2, not at any other time apart from t2. So the Lagrangian description suffers from a drawback that if I did want to know the velocity at this particular point at t naught, I must initialize some particle originating over here at time t naught. I cannot originate a particle over here at t naught and expect me to know the velocity at this particular time. So when this particle moves eventually and reaches over here, say at t10 after 10 time steps, then I can tell that at this particular time, that is at t10, this particular point has a certain velocity. So we are all familiar with this notion of description of velocities in a classical mechanical sense, that is the Lagrangian approach. The Eulerian approach does away with this drawback, and it makes use of the field description for the velocities or the pressures, densities, whatever. So in the Eulerian approach, instead of associating ourselves with a identified particle and following that particle throughout the domain, we sort of choose a lot of points which are fixed in the domain. We will choose a bunch of fixed points in the domain, and we will observe the velocities at these particular points in the domain. So at a given instant of time, the velocity might be something like this over here. At the next instant, it could be something like this. At the next instant, it could be something like this, and so on. How does this framework tie in with the Lagrangian framework? That is one of the questions that we wish to answer. But before that, the Eulerian approach essentially represents everything as a field. So U, V, and W are all uh, fields, meaning U is a function of X, Y, Z, and time. So U at this point can vary, it is smoothly varying, and it can change in time, meaning at a given time these are the velocities at these particular points. At the next time instant it could be something like this. So velocities can change, but we are always focusing our attention at fixed points in space rather than following given material points. So now let us consider a trajectory like this. Suppose at t equal to 0, so these are the two Eulerian points. I have drawn the exaggerated diagram, but these may be close. So let's call this 1 and let's call this as 2. At a given certain instant of time, the velocity is something like this, suppose. Now a particle originates at this point, and because of this particular velocity, it proceeds to go along this trajectory. Now by the time this particle reaches this point, the velocity might change. The velocity can become something like this. Okay, the velocity can become something like this, and let me draw the particle over here. So the change in velocity for the particle, what does the particle actually see its velocity change as? So okay, let me draw this as the yellow vector. The pink vector is the velocity at point 2 at the same time. So let me call this as t naught. And the pink vector was the velocity vector at point 2 at t naught. And the red vector is the velocity at point 2 at time t. So what is the change in velocity experienced by the particle as it moves from point 1 to point 2? So it initially had a velocity like this, and finally it has a velocity as shown in the red, something like this. So while this velocity has changed, the velocity at point 1 might also have changed to something like this. Let me call this velocity at point 1 at time t. So the total change in velocity as seen by the particle, that is v at point 2 minus v at point 1, is essentially me telling that it is the velocity at point 2 at time t minus velocity at point 1 at time t naught. Because at arriving at point 2, the particle will see that it has now taken a certain amount of time to go to this place, and it has now encountered a different velocity. And this change may be written as v2 at time t minus v1 at time t plus v1 at time t minus v1 at time t naught. Essentially, I have added and subtracted v1 at time t. So this means this is equal to v2 at time t minus v1 at time t. This is one combination of terms. So the physical meaning of this is, at a given instant of time, the change in velocity because of a change in location. So this is the difference in velocity at same time but different location. Whereas the other combination of term is this, and this combination is essentially v1 at t minus v1 at t naught. That is the change in velocity over time at the same location. So it is change in velocity at same location, that is location 1, right, over time, meaning at the same location the velocity has changed in time. Now to better understand the physical meaning of this change in velocity, let us say that you are right now at Kharagpur and you want to go to Kolkata, and at this particular point of time the humidity of Kharagpur is 20% and at Kolkata it is 50%. Now you are in this small car and over time you are going from, so this change in altitude of this point represents time. So this is the time axis and this is the distance axis. So as time progresses, you are going from Kharagpur all the way to Kolkata, and during this change in time, the local humidity has maybe changed to 40 over here, and at that same change in time, the humidity has changed in Kolkata from 50% to 70. So what is the total change in humidity that the car has seen? So the car will say this takes 2 hours. I have seen a total change of humidity from 20 to 70 over a span of 2 hours. And this change of 50% over 2 hours is because of the fact that the humidity has changed in time. The humidity has changed in time, and you are going to a different location as well. So it is because of two factors. The first is the difference in humidity at same time over different locations. So at same time, different locations. So what is the change in humidity? It is 70 minus 40. And this corresponds to this particular term. While it is also because of change in humidity at the same location over time. At same location over time. Meaning I am keeping the location fixed, and as time progresses the humidity changes, so it is 40 minus 20. So this term corresponds to this particular term. So total change is 30 plus total change is 20, and this gives us a total change of 50 over 2 hours. Okay, so let us formalize these statements further. Let us formalize these statements further. So V2 at t, so change in velocity as seen from the Lagrangian framework is V2 at t minus V1 at t plus V1 at t minus V1 at t naught, where this is point 1, this is point 2. Now, given that these are all velocities in a field description, I can write down the velocity at point 2 at a given time in terms of the velocity at point 1 at the same time instant. So how will I do this? I will do it by means of a Taylor series expansion. So this will be V2 at time t is equal to V1 at time t plus del V1 del x times dx plus del V1 del y dot dy plus del V1 del z times dz plus del 2V del x2 dx2 by 2 factorial and other higher order terms. So these all will be higher order terms. There will be delta x square, delta x delta y, delta z square, and so on. And thus this particular term, it simplifies to del v1 del x, that is the velocity at point 1 del x delta dx plus del v1 del y dy plus del v1 del z dz. What about this particular term? Let us retain that particular term as it is. So it is simply v1 at t minus v1 at t naught. So delta v Lagrangian divided by delta t essentially becomes del v1 del x dx upon, so instead of writing it as dx, I can better write it as delta x upon delta t plus del v1 upon del y delta y upon delta t plus del v1 del z delta z upon delta t plus terms containing delta x square, delta x, delta y square, and all higher order terms divided by delta t. What will be the additional term? It will be v1 at t minus v1 at t naught divided by delta t. So in the limit delta t goes to 0, delta v Lagrangian by delta t becomes dv dt as seen by the particle at location 1. It is the rate of change of the velocity vector at particle 1. as time goes to 0. That is, points 1 and 2 are merging. As time delta t goes to 0, 2 tends to point 1. And thus, this is the very definition of the velocity of the particle in the classical mechanical sense. But on the right hand side, we have this will be equal to, so now what is delta x upon delta t in the limit? Delta t going to be, it will be the u velocity at point 1. So it will be u del v1 del x plus delta y upon delta t in the limit delta t goes to 0 will be v del v1 del y plus delta z upon delta t as delta t goes to 0 will be w del v1 upon del z. And as delta t goes to 0, delta x, delta y, delta z will also go to 0, and all these higher order terms will vanish, as is the case with any infinitesimal formulation. Lastly, we have v1 at t minus v1 at t naught upon delta t, and this is simply del v1 upon del t. So we are able to express the velocity as seen in the classical mechanics view frame. This is the Lagrangian viewpoint, and able to represent it by means of the Eulerian description. So this particular mapping from the Lagrangian to the Eulerian description is very important in fluid mechanics, and this particular derivative is known as the total derivative. So it is essentially del t of v1 plus u del x of v1 plus v del y of v1 plus w del z of w. And in general, instead of having this velocity vector at point 1, I could have written this same expression. The same derivation also holds true for any scalar or any vector. So I might as well write, so rate of change of say any quantity phi as seen from the Lagrangian framework will be equal to del phi del t plus u del phi del x plus v del phi del y plus w del phi del z. It is very well valid. So in an operator form, I can write this as del t plus u del x plus v del y plus w del z, all operating on the variable phi. So this is an operator way of writing it. And those of you who are very observant, I can write this as del t plus u vector dot nabla acting on phi, because u vector dot nabla will be u del x plus v del y plus w del z, and it is not equal to the divergence of the velocity. This is an operator, this is an operator, while this is a scalar. So this is called as the total derivative, and it is also sometimes called as the material derivative, and it is a very important parameter to know in fluid mechanics. So let's end our lecture over here. We are out of time. Any questions on this so far? So let me, if you have 2 more minutes, the derivation that we just did, it shows that d phi dt as seen from the Lagrangian viewpoint is del phi del t plus u del phi del x plus v del phi del y plus w del phi del z, and this is also the material derivative, total derivative. It is often called as d phi dt, and this capital D is to indicate that this derivative is done in an Eulerian frame. But in the limit delta t goes to 0, the Eulerian viewpoint and the Lagrangian viewpoint merge, and hence there is an equality between the two frames of observation. And all this, all the derivation that we did is simply, one could have simply said that yes, phi is a multivariate variable in an Eulerian viewpoint as a function of x, y and x, y, z and time. So I can write d phi in the Eulerian viewpoint as del phi del t dt plus del phi del x dx plus del phi del y dy plus del phi del z dz. Then I can simply take dt on the left hand side, and this will give me simply del phi del t plus, so dx dt is going to be the u velocity at that point, dy dt is going to be the v velocity at that point, and dz dt is going to be the w velocity at that point. So this kind of train of thought also is valid, but the derivation that we did explicitly brings into the picture the way the velocity has actually changed. So it brings into the temporal component of the derivative, and it clearly brings into picture the advective component. So the derivative of any scalar as seen by a particle traveling in that velocity field is due to the fact that the variable itself can change over time, and the fact that the variable can change over space. And the way we represent the relationship between the change in variable over space with the total derivative is through the operator u dot nabla. Okay guys, I think we are done with today's recording. Let me stop